scans.
I'm Dr.
So
Benjamin
our colleague
Xu
will be
from the
talking on this
University of
issue.
Southern California in Los Angeles. I'd like to thank the symposium organizers for inviting me to speak today about the use of AI in glaucoma imaging. I'd like to acknowledge my funding sources, including the National Institutes of Health, as well as the Glaucoma Research Foundation. I do receive research support from Heidelberg Engineering, and I will be talking about their anterior segment OCT system. Artificial intelligence, or AI, broadly defined, is when computers are taught cognitive functions such as learning and problem solving. AI holds the potential to revolutionize healthcare by increasing accessibility to care and reducing its costs. Deep learning is a popular form of AI. Deep learning has been widely applied to the field of ophthalmology to automate the image analysis for detection or prediction of disease. Detection of patients with glaucoma relies heavily on diagnostic tests. This includes OCT RNFLs, fundus photographs, as well as visual fields. Reliance on diagnostic testing makes glaucoma particularly well suited for deep learning methods. Deep learning has been applied with more success to fundus photographs and OCT RNFLs than visual fields, and I will focus primarily on fundus photographs and OCTs in my talk today. Fundus photographs are useful for detecting a wide range of ocular diseases, such as glaucoma, age-related macular degeneration, and diabetic retinopathy. Fundus photographs are a convenient method for evaluating the optic nerve for structural changes that are suspicious for glaucoma. And an advantage of fundus photography is that the cameras that are used in teleophthalmology settings tend to be fairly low cost. Fundus photographs and deep learning were combined in this landmark 2017 study by Daniel Ting and colleagues that was published in JAMA. In this study, the research group used around 200,000 images, including 2% of the images that were referable glaucoma suspects. The fundus photographs were fed through a convolutional neural network that was trained to classify images as referable or non-referable glaucoma suspects. The performance of this algorithm was excellent. In this receiver operating characteristics curve, we can see sensitivity plotted against 1 minus specificity, and the area under this curve is 0.94, which indicates excellent predictive performance. We can see that for a sensitivity of 96%, specificity was 87%. OCT RNFLs are a popular diagnostic tool for detecting patients with glaucoma. RNFLs can be very useful for identifying focal and diffuse structural damage that is consistent with the diagnosis. In this paper published in JAMA Ophthalmology by Thompson and colleagues in 2020, over 20,000 OCT RNFLs were used to train a convolutional network to classify raw RNFL B scans as either healthy or glaucomatous. Again, the performance of this algorithm was excellent. Here we can see that the orange curve represents the performance of the deep learning algorithm with an area under the curve of 0.96. This is compared to a model based solely on RNFL thickness measures, which had a AUC of 0.87. Let's switch gears for a moment and talk about glaucoma risk factors. When we think about glaucoma risk factors, we often think about age, intraocular pressure, race, family history, and central corneal thickness. However, a very important risk factor that we need to keep in mind here is the status of the angle. That is the angle open or is it closed? Angle closure is a very important risk factor for glaucoma. In angle closure, there is contact between the peripheral iris and the trabecular meshwork. This contact impedes the normal outflow of aqueous from the eye, And when angle closure is severe, it could lead to elevated intraocular pressure and angle closure glaucoma. Primary angle closure glaucoma is a common cause of permanent vision loss worldwide. The condition currently affects around 20 million people, which is around a quarter of all glaucoma cases. The large majority, around 75% of PACG, occurs in Asian regions. Due to aging of the world's population and the importance of age as a risk factor for PACG, the prevalence of this condition is expected to rise rapidly to 34 million by the year 2040. This rise in PACG is concerning as PACG is more visually damaging compared to POAG, conferring a 2.4 times higher odds of blindness compared to POAG. Gonioscopy remains the current clinical standard for evaluating the angle to detect angle closure. When performing gonioscopy, we focus on detecting the pigmented trabecular meshwork. When we can't visualize this key anatomical structure, we tell patients that they have angle closure and may be at risk for angle closure glaucoma. Gonioscopy plays a central role in the glaucoma evaluation, and this is highlighted in the AAO preferred practice patterns. The American Academy of Ophthalmology recommends that gonioscopy should be performed in all patients who are suspected of glaucoma, who are suspected of anatomical narrow angles, or who are being evaluated for incisional glaucoma surgery. Despite being the long-standing clinical standard, gonioscopy has many limitations. It is subjective and expertise dependent, and there's only moderate inter-examiner reproducibility even between trained glaucoma specialists. Gonioscopy can be uncomfortable and time-consuming for some patients, and these limitations have led to gonioscopy being underperformed, at least here in the United States. Fortunately, we have alternatives to gonioscopy for evaluating the angle. These alternatives include anterior segment OCT as well as goniophotographs. Anterior segment OCT technology has evolved rapidly over the last 2 decades. We've moved from relatively slow, low-resolution time domain devices to higher resolution and much faster modern spectral domain and swept source devices. Here's a representative anterior segment OCT image acquired using the swept source Anterion ASOCT system by Heidelberg Engineering. Here we can clearly see the cornea, the angle, the iris, and the lens. One question that my lab asked a few years ago is, can we automate the analysis of these ASOCT images to detect patients who have gonioscopic angle closure? In this 2019 paper, we described deep learning classifiers that could do exactly that. In this study, we used data from the Chinese American Eye study. This is a study, epidemiological population-based study that was conducted here in Los Angeles by USC investigators. And we used about 4,000 anterior segment OCT images from this study. Each ASOCT image was paired with a corresponding gonioscopy grade that was provided by a trained ophthalmologist who performed manual gonioscopy on all participants. We used these gonioscopy grades to classify patients as either angle closure based on the modified Schaefer grading scale grades of 0 or 1, or open angle based on grades of 2, 3, or 4. Here is the ROC curve for the algorithm. And here we can see that it performs very well in detecting angle closure based on a single ASOCT image of a single angle sector. That's the red curve, which has an AUC of 0.93. This corresponds approximately to a balanced sensitivity and specificity of 85%. For detecting angle closure in multiple quadrants, we see that the performance is even better with an AUC of around 0.95 to 96, which corresponds with a balanced sensitivity and specificity of around 90%. More recently, we tested the generalizability of this algorithm as deep learning algorithms often perform worse in independent test data sets and patient populations. In this study, we borrowed data from a community-based clinic in Singapore, and we also acquired data from our own glaucoma clinics at the USC Roski Eye Institute. What we can see here is that despite differences in the locations, patients, practice settings between the different sites, the performance of the algorithm was very similar, with an AUC between 0.89 to 0.92. This would suggest that these types of deep learning approaches, identifying angle closure in ASOCT images, tend to be generalizable across different populations. Up until this point, I've focused primarily on describing AI algorithms that provide qualitative assessment of ASOCT images. That is, algorithms that determine whether an angle is open or closed. However, we more recently have been asking how we can move beyond these types of qualitative assessments in order to provide more precise care for our patients with angle closure. One potential solution is quantitative ASOCT imaging. In order to perform this type of analysis, we have to segment the cornea, iris, and lens, and mark the scleral spurs. After doing so, we can extract measurements of biometric parameters that describe the size, shape, and configuration of anatomical structures in the anterior segment. Recently, we've been conducting research to establish the clinical utility of these types of measurements. In this 2022 paper, we showed that biometric measurements from ASOCT images could predict angle widening after LPI using data from the Zhongshan angle closure prevention trial. More recently, we've been using similar data from the Zhongshan angle closure prevention trial to identify biometric risk factors for progression in both treated as well as untreated PACS eyes. However, one issue with using these types of measurements in a busy clinical environment is that we simply don't have the time to manually analyze ASOCT images in the middle of a busy clinic in order to obtain these types of measurements. Fortunately, AI provides us with a solution to this. In 2020, our lab described a method in which we developed a deep learning algorithm to detect the scleral spur, which is a key anatomical landmark to identify in the biometric analysis of ASOCT images. We used data from the Chinese American Eye study, and we trained a convolutional network to predict the scleral spur location based on its X and Y coordinates. More recently, we have adopted a similar approach and developed a similar algorithm for the Heidelberg Anturion, which is a SWEP source ASOCT system that was recently introduced in Europe and is currently under FDA evaluation. This scatter plot shows the human-human agreement between a reference grader and a trained glaucoma specialist. What we can see here in the scatter plot is the error, which is calculated as the reference minus the predicted scleral spur coordinates. We see that the median error here is around 60 microns. Compare this to the human-machine agreement, and you'll see that the two are very similar. The median error is around 56 microns in this case, which indicates that the agreement between human and machine approximates the agreement between two experts in identifying the scleral spur. This table shows the inter-grader reproducibility of biometric measurements that correspond with these predicted scleral spur locations. We see that there is excellent agreement in all parameters between trained glaucoma specialists that is approximated by the agreement between a glaucoma specialist and a deep learning algorithm. All of these inter-class correlation coefficients, or ICC values, are above 0.95, which indicates excellent correlation. I'd like to provide an overall summary. AI provides us with a powerful tool for detecting patients with or at risk for glaucoma, whether it's through the evaluation of fundus photographs, OCT RNFLs, or anterior segment OCT images. We can automate the detection and evaluation of angle closure eyes using ASOCT images and AI. However, overall, further implementation studies are required before AI can be widely adopted for clinical use in diverse patient populations. I'd like to thank the hard work and contributions by all of the members of my lab who contributed to the work that I presented today. And I'd like to thank you also for your attention today. Thank you very much.